This video is over lesson 90, sets, and it is for my pre-algebra classes. So first of all, a set is a collection of elements. And those elements are often numbers. So a collection of numbers, and each of the numbers is an element. And it is often listed with braces. And so braces are those things like parentheses, but it looks like a little parenthesis with an arrowhead, then another little parenthesis. And then to close it, same idea, just going the other way. Those are braces. So we're going to take a look at a few sets here today, obviously. So first up, we have the set of natural numbers. And so natural numbers are basically your counting numbers. So 1, 2, 3, 4, 5, and on and on and on. So I put braces around that, and that's the set. Now there is a special symbol for the natural numbers, and it actually looks kind of like an N, but you double that diagonal bar there. So that's the symbol for the natural numbers. Our next set is the whole numbers, which the whole numbers are very close to the natural numbers. The only difference is they include 0. So 0, 1, 2, 3, 4, 5, and on and on and on. And as far as I know, the whole numbers do not have any special symbol. I've looked for it, I've hunted for it, I've never been taught it, and I've never found it. So if it has one, it's somewhere out there where it has been very elusive to me. Moving on to the integers. Remember that the integers are the natural numbers, their opposites, and 0. So if I kind of put those in order, their opposites are going to go forever in the negative direction, but then they'll work their way towards the middle, which will be 0, and then we'll head off to the positive direction forever. Those are the integers. And they do have a special symbol. Their special symbol looks a lot like the natural number symbol. Only instead of looking kind of like an N, it looks a bit more like a Z. And my best guess as to why that is would be if you were to kind of straighten out those bars in the middle, it would look like an I. That's my best guess. But that is the symbol for the integers. Next up is the rational numbers. And the rational numbers, kind of an interesting definition. Their definition is A over B such that, so it's a fraction, A over B such that A, and then we have this little symbol here that starts off kind of looking like a U that's been put on its side, and then we put a line in the middle. So it's a kind of, it looks like an E, but it's a bit more curvy, whereas a E typically is a bit more boxy. And so we're going to put our integer symbol after that, because what that little guy there means is it means element of. Element of. So A has to be an element of the integers. So your numerator has to be an integer. B also has to be an element of the integers. So B has to be an element of the integers. And run out a little bit of space here. B cannot equal 0. So your denominator can't be 0. That shouldn't come as any great surprise. The rational numbers, it turns out, do have a symbol here. And so if you think about this definition, a fraction really is a division problem. So what we're saying is rational number is any number that can be written. Okay, it doesn't have to be written currently that way, but it can be written as a fraction with an integer on top and an integer on bottom that's not 0. Well, what's the answer to a division problem? It's a quotient. So the symbol for the rational numbers actually looks like a Q with these 2 extra lines in the middle of it. And so when we see this, think quotient. That's your rational numbers. Think quotient. So next up is the irrational numbers. So ir just means not. So this is x, so some number, such that x is, we got that element symbol, but now we're going to put a slash through it. And it's not an element of the rational numbers. So this symbol here, not an element of. So the irrationals are not rational, which means that you cannot find a fraction using integers that will equal that number. And that leads to some understandings about what an irrational number then must be. So if we consider it can't be any integers, because integers are always themselves over 1. Irrational numbers cannot be your normal fractions or mixed numbers. They can't be terminating decimals, because all terminating decimals can be turned into normal fractions, so an integer over an integer. Likewise, repeating decimals can all be turned into an integer over an integer. So that means that, well, can't be integers. It can't be any fraction or mixed number that we're used to seeing. So it's got to be a decimal. But it can't be a terminating decimal, which means it's infinite. And it can't be a repeating decimal, which means that it's infinite and non-repeating. So irrational numbers would be like pi. They keep going on and on forever, but they never repeat. And finally, that leads us to the real numbers. And the real numbers are actually a union of the rational and irrational. And then here, union is just telling us to combine the sets. So if we take all of the rational numbers and put them together with all the irrational numbers, together that makes the real numbers. And this does have a symbol. It looks like a capital R with that vertical line doubled up. There, of course, are other sets out there. This is just a few of them, some of the more popular, more regularly looked at sets. But we've got some others that are pretty popular as well. For example, the even numbers. So the set of all even numbers, well, you can have negative even numbers. Even is defined as being divisible by 2 and still having an integer. And so this will go forever down into the past. And then as it works its way up, I could have a -6 and -4 and -2. 0 is even. Obviously 2, 4, 6, and on and on and on. Well, if we have a set of even numbers, how about a set of odd numbers? So likewise, they go forever towards the negatives, but then -5, -3, -1, then +1, +3, +5, and on and on and on. And there are so many others out there. So, little look at just elements here. Let's take a few numbers and think through what sets they belong to. So 2, 1/2, and the square root of 2. So first of all, we're just going to look at our sets that have the symbols and make our lives easier. So 2 is a natural number. So it's an element of the natural numbers. 2 is an integer. It is a natural number, the opposite of a natural number, or 0. 2 can be written as a fraction using integers. So therefore, it is a rational number. Specifically 2 over 1, 4 over 2, 6 over 3, negative 10 over negative 5. And then finally, because it is real, it actually exists in our world, we know that 2 is an element of the real numbers. For 1/2, 1/2 is not a counting number, which means that it is not an element of the natural numbers. 1/2 is not a natural number, the opposite of a natural number, or 0. 1/2 is, however, a fraction using integers. 1 is an integer and 2 is an integer. So it is rational. And of course, does 1/2 exist in our real world? Yes, it does. So it's a real number. Last of all, square root of 2. We do not count with the square root of 2, which means that it is not a natural number. It is also not the opposite of a natural number, nor is it 0, so it's not an integer. The square root of 2 does not have a nice square root, which means actually there is no way to write it as a fraction using integers. Does it exist in our real world, though? Yes, it does. So it is a real number. Let's go ahead and flip over. We're going to learn a few new symbols here. So our first new symbol looks kind of like a U that's been turned on its side, but it's bigger than the one that we used for an element. It's more like a capital U leaned on its side. And this symbol here means subset. And so we might use it to say A is a subset of B. So set A is a subset of set B. And so what this would mean then is every element of a subset is in the other set. So if A is a subset of B, this means that every single element of A is also in B. So for example, if I said A equals the set of 1, 2, and 3, and I said B is the set of 0, 1, 2, 3, 4, and 7. So is every element in A also in B? Yes. So what it kind of looks like is it looks like A is just a piece of B. It looks like it got pulled out of B. Well, that's a subset. If we were to look at this in a Venn diagram, sometimes that can be helpful. So we have 0 that only exists in set B. We have 1 that exists in both of them. We have 2 that exists in both of them. 3 that exists in both of them. 4, which is only in B, and 7, which is also only in B. And so in order to be a subset, if A is a subset of B, then this should be empty. And it is. So that everything that A has is also in B. Or another way to visualize this is if A is a subset of B, then A should fit into B. So A has 1, 2, and 3. Are 1, 2, and 3 also a part of B? Yes, they are. But also 0, 4, and 7 are. So A is a subset of B. We're going to move on to our next symbol. Our next symbol here looks like a U again, capital U, but this time it's been turned upside down. And so this time, this means intersection. Means intersection. And so we might write A intersection B. Or another way to say that a little more naturally is the intersection of sets A and B. The intersection of sets A and B. So the intersection of two sets consists of every element that the sets have in common. So in this case, we're going to define A as 1, 3, 6, 7. And we'll define B as 2, 3, 7, and 9. And so if we look at a Venn diagram, that's A, and that's B. So A has 1, but all by itself. It also has 3, which they both have. It has 6, which only it has. And it has 7, which they both have. So over here, 2 is only in B. 3 we already got is both of them. 7 is both of them. 9 is just in B. So when I write A intersect B, or the intersection of A and B, if you grab your orange highlighter here, by saying the intersection, we are only talking about what they have in common. So in a Venn diagram, it would be only this stuff that they both have. So the intersection of A and B here would be 3, 7, 3 and 7. Looking at another example, let's say we have set C, which was 2, 4, 6, and then set D was 1, 3, and 5. So again, Venn diagram can be helpful here. Oh, let's make that a little better. Need some space to actually overlap. That's better. All right, so this is C, that's D. So C has 2 all by itself. C has 4 all by itself. C has 6 all by itself. D has 1 all by itself, and 3 and 5. So remember, ladies and gentlemen, when we write C intersect D. So the intersection of C and D, the intersection here is going to be where they overlap. Well, these two don't overlap. And so we get a set with nothing in it, which can also be written with this symbol here, a circle with a slash through it. And so this guy right here is what's known as the empty set. And then this also is sometimes known as the null set. So empty set, null set. Oh, I'm sorry, I just realized you guys couldn't see that. Sorry, I wasn't watching my screen, guys. All right, so C was 2, 4, 6. D was 1, 3, 5. So in my Venn diagram, 2, 4, 6 are only in C. 1, 3, 5 are only in D. So the intersection is with the overlap. There was no overlap, so we just do 2 braces and it's empty, so an empty set. Or we can use this symbol here, null set, which can also be called an empty set as well. For that matter, this could be called a null set as well. So null set, empty set, there's nothing in there. And that's an intersection. You know, let's come up here and just give this a little separation. And then let's do likewise down here, a little separation. And this brings us to our last concept, which is a U, just as we're used to seeing it. And this is a U for union. So A union B, or more naturally stated, the union of sets A and B. And the union of two sets consists of, and I want to leave this space here for an example, consists of any element in either set. So in other words, if that element is in either one of the sets, it's also part of the union. So if we take a look, we're going to reuse C and D from up there. So if we use the union here, so C, remember, was 2, 4, 6, and D was 1, 3, 5. I'm going to make my Venn diagram a little bit smaller here just because we're running out of space. So that was C, that was D. So 2, 4, 6, 1, 3, 5. You grab your yellow for me this time. So the union of C and D, a union just tells us to go ahead and put the whole thing together. Just put the whole thing together. And so the union actually would be every single element in one set. 1, 2, 3, 4, 5, and 6. That's a union. And that, ladies and gentlemen, is the end of our lesson.